Hi, my name is Mike Sklash. This is the second part of a two-part series on legacy nitrate um, and how it's impacted groundwater. How did this happen? And it's not always what you think. The first part, we talked about the tools that we've used during the past 10 years or so to investigate the legacy nitrate issue and other aspects of nitrate in groundwater. So without further ado, I'm going to present 3 case studies, and these case studies are projects that I worked on for clients, and I appreciate their willingness to allow me to talk about them, but they did ask me not to indicate where the sites were, and the names and places have been changed to um, hide the locations. So this first case study revolves around the background well at a commercial dairy. And we're going to talk about legacy nitrate, nitrate and water isotopes, data loggers, and episodic mounding. So this is our dairy. Here, it's a large dairy. You can actually see on this Google Earth photograph monitoring wells. This is a vegetative treatment area for non-manure contact runoff. These are where the manure is stored temporarily. So the geology generally is sand. The water table depth is about 20 feet below ground level. The groundwater flow direction is shown by that blue arrow from northwest to southeast. And when I got involved, the concept of legacy nitrate was not known. But one of the problems was the background well, where this white dot is. And the background well indicated that the nitrate in groundwater coming onto the site was really low, like a few milligrams per liter, where we knew that the region had high nitrate in the groundwater, in some places 80 milligrams per liter. So we wanted to figure out why that was happening and what we could do about it, because if we didn't get a valid background well to indicate, with comparing it to down gradient wells, like down at the bottom and the right side, that we'd always be showing that the dairy contributed to groundwater contamination. So that was the business consideration in this case study. So we did some travel time analysis using standard methods like hydraulic conductivity and hydraulic gradient, and just to see what would happen to groundwater moving across the site. And really, even though it was a sand, it moved very slowly because the hydraulic gradient wasn't large. First thing we did was look at the nitrate distribution and looked at the nitrate isotope data. And on the left, you see the map in 2016 of the nitrate concentrations in milligrams per liter at several wells. So remember, groundwater is coming from the top left-hand corner. That's the nitrate concentration, so well over the drinking water limit. And then you can see some also in the down gradient part, the right side and the bottom side, already over the down drinking water criterion. So one of the things we wanted to know is, was any of this nitrate due to manure from the dairy? So we did some nitrate isotope analyses, and basically you can see this orange area here. That's the area that we saw before when we talked about methods. This area here would indicate animal waste, and we just don't see that. So this well, MWJ, for example, which has 27 milligrams per liter nitrate, that's from fertilizer, natural soil, and not from animal waste. So what's with the background well, MWH? This is a photo that we took during a large storm in the spring, and this is the VTA, the vegetative treatment area, and you can see it's flooded. It happens to be the lowest area on the dairy, and the monitoring well, background monitoring well, MWH, is right in the lower left-hand corner, just off the screen. So what we did here, you can see MWH up here, groundwater's flowing from top left to bottom right. We looked at the various wells and looked at their water isotope concentration. So O18 against deuterium, and we can see some of the wells, like C is over here and A is over here. And they line up pretty nicely. MWH is a little bit off, but not too bad. And that's our early February meteoric water line, number 1, before the storm. And there's MWH, again, the background well, a little bit out in left field. Then we had the storm on March 16th. Luckily, we had people there. We were able to sample the water, this ponded water, right next to MWH. And this is what we found. That's the O18 deuterium plot. And that's way different from what it was up here and from the other groundwater wells. And we also measured it on the 17th and the 18th. So what's happened is that MWH has changed dramatically because of this flooding. And those values in there have no resemblance to the original groundwater, but they do resemble the ponded water. And this is what we, is our conceptual model, that basically this water ponded, infiltrated, and diluted the water at MWH. So it had very little nitrate in it. MWH had very little nitrate in it. So we wanted to look for further evidence. So what we did was we installed a number of data loggers to get high resolution groundwater level monitoring so that we could see if there was mounding going on due to the flooding in MWH, in the VTA affecting MWH. And we compare that to MWL. And I apologize, these aren't the greatest graphs, but here's MWL. So distant from the VTA ponding, and you can see a change in the water level downward consistently by about 0.6 feet. However, MWH, when the storm occurred, was showing several feet of change. We say that based on both the isotopic data and the water level changes, which were fast and furious when that area flooded, that was episodic mounding. And we went on to conclude that MWH was not a valid background well because it changed and didn't represent the water coming onto the site. It represented rain-diluted groundwater. And we were able to change the background wells. So the bottom lines for case study 1, legacy nitrate underlies the site, and it's not dairy related. The background well, MWH, was diluted by rapid recharge at the flooded VTA. There's episodic mounding at that background well, so we had to change the background well. And in fact, we were able to change it to be much more representative of those high nitrates coming in. So the client was pretty happy about that, so that it was a more realistic picture of what was happening coming onto the dairy and going under the dairy and coming off the dairy. The second case study involved another large dairy that you can see here, and residential wells that were largely along this lake, and they had nitrate impact in their water wells that were screened at about 50 feet below ground level, and immediately pointed their finger at the dairy as the cause of that. So we're going to look at legacy nitrate, nitrate isotopes, tritium, high resolution monitoring, and HPT in this case study. So the dairy was established in 2007. So could manure impacted groundwater reach these residential wells? Well, we evaluated that. So we looked at the geology again. Geology here was thick sandy soil, water table about 20 some feet below ground. Groundwater flow direction was from top left to bottom right, northwest to southeast. Nobody considered legacy nitrate as a possibility for the problems encountered by these residential wells. And the business consideration was the dairy didn't think they were responsible for it because simple calculations showed that the groundwater couldn't move that far, but had to go through the process. So we monitored this irrigated property, and here the groundwater is flowing this way. We had 3 locations that we did some high resolution monitoring and isotopic analysis to see what was in the groundwater and what that meant with relationship to could the dairy be the cause of the residential problems. And just to show you that I had an important job, I was there to scare people away from the equipment. And I think I did a pretty good. So just as an example, this is our site number 1. What we did was we knocked down the crop that was growing, corn, about 70 feet into the irrigated circle. We put in these 3 devices. They're suction lysimeters. They sample groundwater from the unsaturated zone or water from the unsaturated zone. DHPT1 was the HPT log. There was in the literature indications there could be a clay layer that might affect interpretation of the results. And we also sampled groundwater at high resolution below the water table. There were already existing conventional wells that were shallow water table well, medium depth, and the deep well would have been about 80 feet. So this is us putting in a suction lysimeter. So basically it's a PVC pipe, and the bottom has a unglazed porous ceramic cup. You evacuate it, as you can see in here. We're pumping out the suction lysimeter, and that sucks in the water from the unsaturated zone. And here's the HPT slide that you would have seen in part 1. So we're trying to look at the geology there. This is our DSPs, are very close together groundwater samples with depth. And we also did sampling of the conventional wells and hydraulic conductivity. So just looking at the vertical profile in tritium, if you remember back to part one, we assume that groundwater doesn't mix vertically. It moves laterally from the recharge to the discharge area. And you can see at site one, the tritium concentration with depth and the tritium concentration. And this is what we see once we get about 10 feet below the water table. Most of the values are 4 tritium units or so above, 4 tritium units, I should say. And that's the irrigation well, the one in the middle. And where do you get 4 tritium units in age-dated tritium data? You have to go back to here, or here, or here. So the dairy was built in 2007, which is up in here. So, you know, it's just possible that that one might slip in, but more likely the groundwater is from that age, like the mid-90s. We looked at whether there was animal waste coming from the dairy, and you can see that there was only one value, DSP 160, so that's at 60 feet. And what we think there is that that sample was being denitrified, whereas most of the values were on the order of like 5 to 7. So that would put you in here, soil nitrate, as you can see. So it doesn't look like the water beneath this site is of an age that could contribute to the residential area. The nitrate doesn't come from animal waste. And our bottom lines were, it's legacy nitrate. It's underlying the site. It's not dairy related. The groundwater at the residential well depth is older than the dairy. And our multidisciplinary approach to this case put our client in a favorable position. The final case study, case number 3, is another commercial dairy. We're going to talk about legacy nitrate, nitrate and water isotopes, and a surprise in this one. So the geology here is a little bit different. It's glacial till that's maybe 10 to 15 feet thick over bedrock. And the water table depth is about, it varies, 15 feet, 10 feet, 15 feet. Groundwater flow direction is from, shown in these, with these blue arrows, basically left to right or west to east. The designated background well was this one here, monitoring well B. And based on our investigation, we found that this site had legacy nitrate under it, which means that it couldn't have come from this this dairy, which is fairly recently. So here's the distribution of nitrate in May 2022. We've got these high levels of nitrate on the east side, low levels on the west side. So how did that get there? That's the groundwater flow as we knew it. We did some travel time analysis, and based on hydraulic conductivity and hydraulic gradient, about 14 years to move across the site. On the north part, and almost 60 years on the south part. So this water here, would have to be really quite old. Um, and this whole area is agricultural. Lots of fertilizer used in the upgrade area. So what we wanted to do was to find out really what was going on. We looked at these two upgradient wells, A and B, and you can see they behave very differently. B, we think even the groundwater wasn't even flowing to the right or the east. But A had some fairly high values. And we looked at tritium. So there were two supply wells on the site. They were deep, hundreds of feet deep, and they're showing very old water. So this would be like pre-1950-ish water. The ponds, we tried to squeeze the manure to get water out. It was semi-successful. And we looked at these various wells. So the one thing you can see here is that all of these wells are pretty much in the same range, about 4.5 to 5.8. The only one that's out of line is MWD. And when we look at that for age, that puts it down here in the early 2000s, and that's prior to when the dairy was established. So the tritium indicates that the groundwater that has the high nitrate on the down gradient side is not related to the dairy. We looked at the nitrate concentrations, and we wanted to get more details, so we added some temporary wells where we just went in, drilled, grabbed a sample, and sealed the hole. And what we found, that there were a couple indicating animal waste. This one up here, which, it's kind of up gradient, and MWD, which is kind of odd. You can see N, which is down. It's there in the middle of the site. Looks like it's denitrified. But all in all, it doesn't look like MWF or G is related to animal waste. But what we did find when we looked at the chloride and nitrate, the temporary wells, was we had a second plume going through this site, not just a regional groundwater flow with nitrate in it, but a second one. And we asked some questions, found out that there was an old toilet in this building, and this building predated the dairy and was not used. This toilet wasn't used. And a little further digging, literally and figuratively, and found that there was wastewater from the toilet on the south side of the building, and there was tile drain that ran to the front. So we found that there were two different types of legacy nitrate at this site. One was the regional legacy nitrate. The second was this toilet that was on the west side of the road, on the other side of the dairy. So we're still trying to figure out what the new background wells need to be, but using these various approaches allowed us to better understand what's going on at the dairy and make some decisions. So the bottom lines for all these case studies is legacy nitrate is a widespread issue. It may be a permit issue. It may be a fine issue. It may be a litigation issue. But you should know that you can distinguish legacy nitrate using nitrate isotopes. You can age date the groundwater with tritium or other methods. You can get an idea of where the water is moving with oxygen and hydrogen isotopes in the water. High resolution monitoring helps, and multiple lines of evidence help. So thank you for listening. Um, Again, my name is Mike Sklash. I'm with the Dragon Corporation and nitrate impacted groundwater. How did this happen? It's not always what you think.